Welcome to a deep dive. Today, we're plunging into something really fundamental to the current AI explosion you're seeing everywhere, the transformer architecture.
That's right. You've given us some incredible source material on this, and our mission for this deep dive is to really unpack what happens inside these models.
Yeah, let's get into it. Specifically, we want to focus on those initial steps, right? Processing text, the kind of thing that makes ChatGPT work.
Exactly.
And speaking of ChatGPT, we hear that GPT acronym constantly. Based on the source, let's quickly break it down. G is for generative.
Yep, it creates new text. P is for pre-trained, meaning it learned from a truly massive data set.
Huge amounts of data, but you can still fine-tune it. Yeah.
Oh yeah, definitely, for specific tasks. And then T,
That's our main topic today, transformer.
the specific neural network architecture. The source makes it pretty clear this is the core invention that really kicked off this recent boom.
It's everywhere now.
It is. And while we're focusing on text models today, it's worth remembering, like the source points out, transformers aren't just for text.
Right, things like DALL-E, Midjourney, text-to-image.
Those two. And their origin, actually, was in language translation back in 2017.
Okay, so how do we even start to get our heads around something this complex?
Well, the plan is to follow the data, step by step through the model. We need to build up some foundational concepts first.
Lay the groundwork.
Exactly. Before we get to what the source calls the heart of the transformer later on.
Yeah.
Think of this as understanding the essential building blocks.
Makes sense. So where do we start? Machine learning basics.
Let's set the stage with that core idea, yeah.
Yeah.
Machine learning, specifically deep learning, as described in your sources. It's a different way of thinking compared to traditional programming.
Right. Instead of writing out every single instruction.
You design a flexible structure, a neural network, and it's filled with billions, literally billions of tunable parameters, often called weights.
Billions of little knobs to tweak.
Kind of, yeah. And then you feed this structure just enormous amounts of data examples.
And the algorithm learns.
An algorithm trains it. Yes, it automatically adjusts those weights, those knobs, until the network figures out how to do the task you want, like predicting the next word in a sentence.
The scale is just wild. The source mentioned GPT-3, 175 billion parameters.
Mind-boggling, isn't it? 175 billion. And that scale is directly linked to the architecture.
How so?
Well, for deep learning models to handle all this and train efficiently using algorithms like backpropagation, everything has to be standardized.
Yeah.
Inputs, intermediate steps. It all has to be formatted as arrays of numbers.
Tensors.
Tensors, exactly. And the parameters, the weights, they mostly interact with the data through weighted sums, which computationally means matrix multiplications. Lots and lots of matrix multiplications.
Okay, so everything's numbers and matrices. Understanding that format is key.
It really is key to why transformers are built the way they are.
Got it. And just to be clear, the weights, those billions of numbers, that's the model's brain, learned during training.
Right, that's the fixed knowledge, more or less.
And the data is the specific input, like the sentence you type in right now.
Precisely. The weights stay, the data flows through.
Okay, structure established. So what's the very first step when text goes in?
The source explains it starts with breaking the input text into smaller pieces. These are called tokens.
Tokens. Are they always whole words?
Not necessarily. They can be whole words, sometimes parts of words, punctuation, even special symbols the model uses.
Okay, so you have these tokens. What's next?
The immediate next step is converting each token into a vector.
A list of numbers again?
Yep, a list of numbers. And the idea is that this list, this vector, somehow encodes the meaning of that specific token.
How does it get that meaning?
That's where the first major learned component comes in. The embedding matrix, usually called WE.
The embedding matrix.
The source describes it like a giant lookup table, or maybe a dictionary. The model has a fixed vocabulary, right? All the tokens it knows. For GPT-3, that was around 50,000 tokens.
50,257, the source said.
Right, very precise. So this embedding matrix has a row, or you can think of it as a column, for every single one of those 50,257 tokens.
And each row is the vector.
Each row is the vector for that token, a long list of numbers. And crucially, the values in that matrix, the numbers making up those vectors, they're weights. They were learned during the training process.
And these aren't short lists. You mentioned high dimensional.
Oh yeah, really high. For GPT-3, the source says these embedding vectors were 12,288 dimensions long.
12,000 numbers just to represent one token, like the or cat.
Exactly. It seems like overkill, but that high dimensionality gives the model a lot of space to work with.
Space for what?
Well, this is what's truly fascinating and a core insight from the source.
Right.
What the training process actually does to these vectors, it arranges them in this 12,000 dimensional space so that directions and distances start to mean something,
Means something how?
like words with similar meanings. The source mentioned different types of towers. Their vectors end up physically close to each other in this abstract space.
Okay, that makes sense. Proximity equals similarity.
Right. But it goes further. The directions between vectors capture relationships. The classic example, which the source notes is maybe not perfectly precise for queen, but works well for family relations, is king minus man plus woman gets you close to queen.
Whoa. So the vector math itself mirrors the concepts.
It seems to.
Mm.
Or think about the geopolitical examples. Italy minus Germany plus Hitler landing near Mussolini. It's learned these historical or national associations.
That's kind of wild.
Isn't it?
Yeah.
My favorite from the source was the cultural one. Germany minus Japan plus sushi.
Don't tell me. Bratwurst.
Lands you near Bratwurst. It picks up on these, cultural stereotypes or common associations present in the training data.
And then there was a weird one. Cat near beast and monster.
Yeah, that was a bit more mysterious. Shows you the learned relationships aren't always intuitive or what we'd expect.
So how do we actually measure these relationships if we want to check if king is close to queen or whatever?
The source highlights the dot product. It's a fundamental operation in linear algebra.
Dot product. Okay.
Geometrically, it tells you how much two vectors point in the same direction. Are they aligned? Computationally, it's pretty simple. You multiply corresponding numbers into two vectors and sum them up. A weighted sum again.
So high dot product means they're pointing similarly. Low or negative means they're not.
Exactly. And the source gives that great example using plurality. You can figure out the vector that represents the difference between cats and cat, like a plurality direction.
Okay.
Then you take the dot product of that plurality vector with any other word vector. If the word is plural, like dogs, you'll get a high dot product. If it's singular, like dog, you'll get a low one.
So you can literally measure pluralness with a dot product calculation.
That's the idea. It lets you probe the semantic structure the model has learned inside these vectors. Pretty neat.
It really is. So this embedding matrix, this lookup table, it's clearly important and it's big parameter-wise.
Oh, yes. For GPT-3, with its roughly 50K vocabulary and 12K dimensions per vector, that matrix alone accounts for about 617 million weights.
617 million just for the input lookup. We're already racking up the numbers.
We are. And it's crucial to remember, as the source emphasizes, at this stage, right after the embedding lookup, each vector only knows about its own token.
It doesn't know the other words in the sentence yet.
Not at all. Bank might mean riverbank or financial bank. The vector is the same initially. The whole point of the rest of the network is to let these vectors interact and soak in that context.
Okay, so context comes later. Now, does the model handle infinitely long text?
No, there's a limit. It processes a fixed sequence of these token vectors at a time, determined by its context size or context window.
Ah, right. The source mentioned 2048 tokens for GPT-3.
Exactly. That's the maximum length of text sequence it can look at simultaneously when making a prediction.
Which explains why older chatbots might, lose the thread in a really long chat.
Precisely. The earlier parts of the conversation fall outside that window.
So this sequence of, say, up to 2048 vectors goes into the main network.
Yep, it flows through multiple layers. The source mentions these layers contain crucial components like attention blocks.
Attention, that sounds important.
It's the key innovation, really. That's where vectors finally get to interact and update their meaning based on the surrounding words, figuring out which model we mean, machine learning or fashion.
Okay, so attention handles the context, and there are other blocks too.
Yeah, things like multi-layer perceptrons or MLPs. They do further processing on each vector individually after it's gathered context from attention. But we'll dive deep into attention later.
Got it. So let's skip ahead then. Assume the vectors have gone through all these layers, they've soaked in the context. What happens at the very end? How does it actually predict the next word?
Okay, so for generating text, we usually focus on the very last vector in the sequence coming out of the final layer. This vector should now, hopefully, encode information about the entire preceding sequence and what's likely to come next.
This final context-rich vector.
Right. And this vector is then fed into another huge matrix, the unembedding matrix, often called WU.
Unembedding, so the reverse of the first step.
Essentially, yes.
Okay.
Its job is to take that single, high-dimensional vector, 12,288 dimensions again for GPT-3, and transform it into a much longer list of numbers.
How long?
One number for every single token in the model's vocabulary. So back to 50,257 values for GPT-3.
Whoa. So it goes from one dense meaning vector to a score for every possible word.
Exactly. And this unembedding matrix is also massive, roughly the same size as the embedding matrix, actually. Another 617 million weights or so.
So just the input embedding and the output unembedding, that's already over 1.2 billion parameter.
Significant chunks of the model are just these input-output mappings.
Okay, so we have this list of 50,000 odd scores. Are those probabilities?
Not yet. They're raw, unnormalized values, often called logits. A higher logit for a particular token just means the model thinks that token is more likely to be the next one.
Logits. Got it. We need actual probabilities, right? Numbers between 0 and 1 that add up to 1.
Precisely. We need a valid probability distribution over the entire vocabulary. And the standard way to do that is using a function called softmax.
Softmax, what does it do?
It takes that list of logits and, well, it kind of exaggerates the differences. The logits that were already large become probabilities very close to 1. The logits that were small become probabilities very close to 0.
So it sharpens the prediction, makes the most likely options stand out even more.
Exactly. It mathematically transforms the logits into that clean probability distribution we need. It involves raising e to the power of each logit and then normalizing by the sum. But the effect is that sharpening.
Okay, softmax gives us probabilities. Is that it?
Almost. There's one more fascinating knob we can turn, which the source highlights. Temperature, usually written as T.
Temperature, like...
Sort of metaphorically. It's an optional parameter you can apply, often during or right after the softmax calculation, and it changes the shape of that final probability distribution.
How does it change the shape?
Well, a standard temperature is 1, which doesn't change anything. But if you set a higher temperature, say 1.5 or 2, it makes the distribution flatter.
Flatter, meaning less difference between high and low probabilities.
Exactly. It gives more probability weight back to the tokens that originally had lower logits. So the model becomes more likely to pick a less obvious, perhaps more surprising or creative next word.
So higher temperature means more randomness, more variety.
Yeah, potentially more varied, maybe more creative, but also potentially more nonsensical if you push it too high. The source mentions the GPT-3 API limits it to 2, for instance.
And lower temperature, below 1.
That is the opposite. It makes the distribution even sharper. The highest probability tokens get even more likely, and the less likely ones become vanishingly rare.
So very low temperature means very predictable text.
Very predictable. If you set temperature all the way to 0, the model only ever picks the single token with the absolute highest logit. No randomness at all.
The source had those story examples, right? Temperature was coherent, but maybe boring.
Yeah, predictable, maybe a bit trite. While a higher temperature story started interestingly, but could quickly go off the rails into incoherence.
So temperature is a way to control the creativity versus coherence trade-off.
That's a great way to put it. It really shows that the model isn't just predicting one next word, but calculating a whole landscape of possibilities. And temperature lets us decide how much we want to explore the less likely paths.
Okay, wow. So putting it all together then, how does the model actually write something longer, like a paragraph or a story?
It's an iterative process. You start with some initial text, maybe just a prompt.
Like once upon a time.
Exactly. You feed that into the whole pipeline we just discussed, tokenize it, get the embeddings, run it through all the network layers.
Including attention and MLPs?
Right. Then you take that final vector, run it through the unembedding matrix to get logits for all possible next tokens.
Apply softmax, maybe tweak with the temperature.
To get your final probability distribution over the entire vocabulary. Then you sample. You computationally roll the dice, according to those probabilities, and pick one token. Let's say it picks there.
Okay.
You append that chosen token there to your original text. So now you have once upon a time there.
Ah, I see. And then you feed that new, slightly longer text back into the model.
Exactly. And repeat the whole process. Predict the next token after there. Maybe it picks was. Now you have once upon a time there was. Feed that back in.
And it just keeps going, predicting one token at a time, adding it, and looping.
That's the fundamental generation loop. That step-by-step, token-by-token prediction is what you're seeing happen in real time with chatbots like ChatGPT.
So a basic chatbot is just this process, maybe with some initial instructions.
Pretty much. You often start with a system prompt, hidden text that sets the stage, like you're a helpful AI assistant designed to answer questions. You put that before the user's actual query.
And then the model just predicts the next part of the conversation, turn by turn.
Using this same generation loop, yeah. always considering the conversation history up to its context limit.
Okay, that actually pulls together the beginning and the end really nicely.
Right, we covered quite a bit of ground there.
We definitely did. From raw text becoming tokens, then these high-dimensional vectors via the embedding matrix.
Learned vectors, where space and direction actually encode semantic meaning, which is still amazing.
Yeah, probing that with dot products, and then jumping to the end, the final vector getting mapped back via the unembedding matrix to scores, the logits.
Which softmax turns into probabilities, and temperature lets us shape that distribution.
It feels like we've covered the essential inputs and outputs. These pieces, tokens, embeddings, vectors, matrices, weights, dot products, unembedding, softmax, logits, temperature, they seem like the absolute fundamentals you need to grasp.
They really are. The source calls this the necessary groundwork, the wax on, wax off, like in Karate Kid.
Right. The foundational
But
training,
before you can really understand the tricky stuff in the middle.
which is that attention mechanism we keep mentioning.
Exactly, because that's where the magic of context happens, where those initial isolated token vectors finally get to communicate and figure out what the sentence actually means as a whole. The source calls it the heart of the transformer for a reason.
So understanding everything today, the embeddings, the output layer, the probabilities, that's essential prep for tackling attention.
Couldn't have said it better myself.
It really makes you think, though, this whole process, it sounds so mechanical. Convert to numbers, multiply matrices, get scores, pick the highest probability. Yet the result is coherent text, sometimes creative text.
It's the scale and the patterns learned across trillions of words of input data that allows complexity to emerge from those relatively simple operations repeated billions of times.
So just thinking about what we covered today, based purely on the source, what's a final thought to leave people with?
Well, maybe consider this. How does the model manage to bake so much potential meaning and relationship information into those initial embedding vectors? And what does it truly imply that directions in that high-dimensional space can capture things like nationality or plurality? It suggests a hidden geometric structure to language itself, discovered by the model.
Or maybe think about the output side. How does simply predicting the statistically most likely next token over and over lead to coherent paragraphs and stories? And what does the fact that we can use temperature to dial between predictable and creative tell us about the nature of the knowledge stored in those logits even before the final choice is made? What possibilities is the model truly considering?